Problem 2.1 asks us to prove a series of 3 theorems. So let's start right away with number 1. For normalizable solutions, the separation constant E must be real. So, and then the hint is to write E as E naught plus I big tau, with E naught and tau being real, and show that if equation 1.20 is to hold for all of t, then big tau must be 0. So let's sort of take this apart bit by bit. First off, the separation constant E, the fact that we're referring to a separation constant here implies that we are dealing with separable solutions. So let's just sort of write that out right away. So the fact that we have a separation constant E means that our psi of x comma t is going to be in the form of a separable solution. So it's going to be equal to little psi of x multiplied by our exponential time function, so e to the power of negative I times e times t, all divided by h bar. Okay, so for normalizable solutions, the separation constant e must be real, and we want to show this. So the hint here is for us to start off by writing e as an imaginary / complex number, E naught plus I tau. So let's do that right away and see what this gives us. So this is going to be equal to psi of x is not going to change. It's just going to remain as before. Now we have e to the power of negative I times t, and then multiplied by E naught plus I times tau, all divided by h bar. And from here, we can sort of make a few simplifications, make this a little bit easier to read. So this is going to be equal to little psi of x multiplied by, and here, since exponentials with their powers being added on can be replaced with products, we can say e to the, whoops, that is a very horrible e, my apologies. We can say e to the power of negative I times E naught t all over h bar, and we're going to multiply this by e to the power of, whoops, e to the power of, and here we have negative I multiplied by a positive I, so that just becomes positive, so e to the power of t, or tau times t all over h bar. And from here we want to show that these solutions cannot be normalizable, because our original goal is that we want to say that for any solution that is normalizable, E must be real. So in this case, we have a counterexample where E is not real, so therefore we must show that this is not a normalizable solution. Well, in normalization, what we want to do is we want to show that the integral of the magnitude of our wave function psi squared dx over all of space, being from negative infinity to positive infinity, must equal 1, because probabilities can only add up to 100%. They cannot be added to anything else. Now, let's say if this is true, we can look at this. We say that, well, okay, in that case, if we try and sort of use this instead, then we have an integral from negative infinity to positive infinity of little psi of x remains the same, so it's just going to be the magnitude of little psi squared, and then e to the negative I E naught t all over h bar, and then we're taking the magnitude squared of this second term, so we multiply it by a positive version, so e to the positive I E naught t over h bar, and then finally the magnitude squared of the third term, which does not have an imaginary, so we don't have to multiply by the conjugate, so this just becomes this thing squared, or since it's an exponential, we can just write it as e to the 2 times tau times time divided by h bar, and this is all towards dx. Now, easily. These two cancel out instantly because they are the same power of e, just with a different sign. They just cancel automatically 1. So this becomes the integral from negative infinity to positive infinity of the magnitude of psi squared, or little psi squared, times e to the 2. In fact, we can just move that out of our integral because there's no sort of there's no x dependency on that, and we're going to write it in red here, e to the 2 tau times time divided by h bar. And from here we've basically finished our proof, because this automatically goes to 1. However, this does not go to 1, because e to the 2 tau t over h bar, well, the only way that this goes to 1 is if this tau sign, or if this tau constant goes to 0, because then you have e to the power of 0, which is just 1. If tau is any other value, then this will never equal, well, this might equal 1 for one point in time, but it will not equal 1 for any other point in time. Therefore, this solution is not normalizable. We cannot possibly enforce this requirement of the magnitude squared integrating over all of space to 1, because we have this extra e to the 2 tau t over h bar here that will not equal 1 except for very specific times, and it generally is not enough. So we have finished part A. The second theorem is a bit of a doozy, so let's take this slowly. The time-independent wave function, little psi of x, can always be taken to be real. So little psi of x is this thing that we've been working with all this time when we deal with separable solutions. Apparently, it is always real, according to Griffiths, or it can always be taken to be real, in contrast to the full wave solution, big psi of x comma t, which is necessarily complex. We don't exactly know the proof to show that this is true, but we can just take Griffith's word for the purpose of this problem. Now, moving on, that doesn't mean that every solution to the time-independent Schrödinger equation is real. So what we're saying is that psi of x can be either real or imaginary. This little psi time-independent, x-dependent function can either be real or imaginary. However, what it says is that if you've got one that is not real, it can always be expressed as a linear combination of solutions that are. So what we're saying is that psi of x can be real or it can be imaginary. However, if it is imaginary, we can always rewrite it as a linear combination of real solutions, all with the same associated energy value of E, which is our separation constant, and have that still be valid. So as a result of that, we actually don't have to ever write little psi of x as a complex function. So you might as well stick to little psi's that are real. So this is what we're trying to prove, and it seems a little bit intimidating because of this big chunk of text, but it really is not as bad as it seems. So let's look at the hint. If little psi of x satisfies equation 2.5. 2.5 is the time-independent linear equation, or the time-independent wave function equation for little psi. For a given e, so too does its complex conjugate. Let's sort of look at this very first sentence and sort of unpack what it means. So equation 2.5 is basically just the form of the time-independent wave function solution for little psi. So let's write that down. Equation 2.5 says that negative h bar squared divided by 2m multiplied by the second derivative of little psi with respect to x added with the potential v, which we assume to be purely x dependent as well, not time dependent, multiplied by little psi must equal our separation constant E, which we have taken before to equal energy, multiplied by little psi. So this is sort of our time-independent wave function solution. So what this says is, okay, let's say we have a little psi that satisfies this solution. The hint states that if psi of x satisfies this equation, then so too does its complex conjugate. And we see here that this is true because this function has no imaginary terms in it. So if I took the complex conjugate of this entire thing, I would get negative h bar squared divided by 2m times the second derivative, this time of psi star, with respect to x squared plus our time-independent potential multiplied by our conjugate psi star is equal to our separation constant, or energy, E, multiplied by psi star. So what we have here is that these two are effectively the same solution, with the only difference being that psi is being replaced with psi star. Therefore, psi and psi star are both valid solutions to our time-independent equation. This is not the same as in the Schrodinger equation, where some of these terms did have imaginaries, and when we took the complex conjugate of everything to get psi star in the Schrodinger equation, certain terms would actually end up reversing their signage. So in that case, the equation would change. But in this case, these two equations are effectively identical, with the only difference being that psi has been replaced by psi star. There's no other sort of sign changes or anything else going on. So therefore, psi and psi star are both valid solutions to our time-independent solution. Now that I've shown that both psi and psi star respectively are valid solutions, the next thing we can enforce is the next part of the hint. For a given E, so too does this complex conjugate, and hence also the real linear combination psi plus psi star and I times psi minus psi star. So let's ignore the I for now and just sort of enforce this idea. So we have psi and psi star both as valid solutions. The next thing I'm going to claim is that from here we can show that psi plus psi star is a valid solution, and so is psi minus psi star. And sort of hopefully you can see that just going in instantly, but if you don't see it, what's happening here is that if we replace all of these psi's and psi stars in this respective equation with this either psi plus psi star or psi minus psi star, everything is just going to distribute out, and because of that we still get a valid solution. And just to sort of emphasize this, let's write this out. So negative h bar squared over 2m times, and here the derivative just sort of distributes in, so we're going to get second derivative of psi with respect to x squared plus or minus the second derivative of psi star with respect to x squared and then we add our potential V multiplied by psi plus minus psi star and this is equivalent to our separation constant, or energy, E multiplied by psi plus minus psi star. And hopefully you should instantly see that this is still a true solution, because what we get here is basically all that's going to happen is if we sort of distribute this out fully and write out our equation in full, what we're going to get is we're going to get sort of this expression plus this expression, and it's equal to these two expressions. So what'll happen is we just combine these two solutions together. It's still true because well, let's sort of write this out. If we sort of write this out fully, then what we're going to get is that this expression sort of added, and let's include this in parentheses, this expression added to the bottom expression is equal to this expression added with this expression. And obviously this is still true, because all we've done is that we have sort of this expression being linked to this term, and we have this expression being linked to this term. All we've done is we've just added a bunch of terms together. So this is still necessarily true. And as sort of a result, well, this is only true for the plus case. In the minus case, the signs would be reversed, but it's still sort of the same idea in that everything is sort of just being carried over and added onto each other. So this equation is still fundamentally true. So because of that, we can say that sort of psi plus psi star and psi minus psi star are still sort of valid solutions to our time independent wave function solution. All right, now that we've proven this, the next thing we can do is let's show that actually psi can in fact always be written as real. So let's consider a complex psi. Let's consider a psi that is written as a plus ib. And respectively, its complex conjugate, psi star, is going to be written as, a minus ib. So hopefully you see where this is going. If I enforce psi plus psi star, well, okay, so let's say we know that psi is a solution to our function. We also know that psi star is a solution to our function. So as a result of that, psi plus psi star and psi minus psi star are also solutions to our function. Well, psi plus psi star, well, that's just equal to a plus ib plus a minus ib. So that's just 2a. And this is real. In contrast, if we wanted to get the b version, well, psi minus psi star is going to be equal to a plus ib minus a plus ib. So this is just 2ib. And if we sort of if we make the additional sort of assignment of multiplying an I term at the front, then this solution is just going to become negative 2b, which is also real. So let's go over this. This first term we have shown is a valid solution. We have shown that psi minus psi star is a valid solution. However, we don't know if I times psi minus psi star is a valid solution. If this is also a valid solution, then this would also be a valid solution, in which case we would be done with our proof. We can always, given some complex psi, write it as either this top form or this bottom form, and as a result of that, give us a valid solution that is real despite psi itself being complex. So our final step is just to show that adding an I term at the front still ensures that this solution is valid. And obviously it is, because we have this time-independent solution here. If I just literally replace it with psi, we've already shown that replacing psi star or psi with psi minus psi star, then this expression is still valid. And I just realized I forgot to cap off this parentheses. I apologize. And if we sort of add an imaginary term or multiply an imaginary term, all that's happening is that each of these terms get an imaginary in front of them. So there's an I here, there's an I here, and let's add the I over here. And since I is sort of added onto each of these terms, it becomes trivial because we can literally just cancel them out. You know, we can divide everything here by I and everything will be canceled out, and this is still a valid solution. So therefore, I multiplied by psi minus psi star is still valid, and as a result of that, we have finished our proof. Given any psi, we can always, if it's constant, if it's a complex number, we can always rewrite it in one of these two forms, and as a result of that, we end up with an equally valid solution that is no longer an imaginary or complex number. For part C, we want to say that if v of x is an even function, that is v of negative x equals v of x, then little psi of x can always be taken to be either an even or odd function. And we don't even need the hint for here, because this solution, now that we've already sort of solved part B, C is effectively analogous. So let's start off, as always, by sort of writing out the time-independent solution, as before. So this is our time-dependent solution. Well, if we replace, and actually there's a few things we have to add here. Psi of x with respect to x squared, and let's move this sort of over, psi of x times psi of x. And what this is telling us is, and this is true, v is an even function. So if we change x to negative x in all of our x-dependent functions, which is little psi and v, then v remains unchanged. However, x, or psi of x, will go from psi of positive x to psi of negative x. So what we can alternatively write is that negative h bar squared over 2m times d2 psi of negative x with respect to x squared plus, and then v is just unchanged because it's even, so going from v of x to v of negative x sort of is effectively the same thing as not changing it at all, since v of negative x equals v of x, times psi of negative x equals e times psi of negative x. And here we sort of have the exact same solution as we did in part B, or the exact same scenario, where we have psi of x and psi of negative x as valid solutions. And in the exact same vein, the combination of psi of x plus psi of negative x is going to be a valid solution. And in the same vein, psi of x minus psi of negative x is also going to be valid solutions to this. And we've already proven this in part B. We've proven that given two valid solutions, psi of x and psi of negative x, or in the other case, psi normal and psi star, we can just write their sums and differences as also equally valid solutions to this time-independent solution, or to this time-independent wave function. So, evidently, from this point, we've pretty much solved it, because this function is even. Because if we sort of replace the signage from x to negative x, then this front term becomes psi of negative x, and this back term becomes psi of x. So all we've done is just these two have reversed orders. And since addition is commutative, it's still the same. And in contrast, this function is odd. And hopefully this is also obvious. If we switch x to negative x, then this bottom term becomes sine of positive x, and this left term becomes sine of negative x. So all we've done is reverse the order. However, the subtraction here still sort of remains. So because of that, we now have reversed the sign of this expression. So therefore, this expression must be odd. So as a result, given an even v of x, we can always write our respective psi of x as either an even function, psi of x plus psi of negative x, or an odd function, psi of x minus psi of negative x. And as a result, we have finished the proof.